Hi students, welcome to this session here at Infinity Learn by Sri Chaitanya. I'm Aniruddha, your physics faculty, and today we're doing a quick take on finding the electric flux. Now this you get introduced to in the chapter Electric Charges and Fields, and this comes right before Gauss Law. So in this session we learn about how to find the electric flux both by the two methods. You have the Gauss Law method and the basic definition method, and we'll also look at a few cases and how you find the electric flux linked in each case. So let's move ahead. First up, the most basic form of finding the electric flux is through its original equation, which is the very definition of flux, which says phi is equal to E into A. Now this is obviously the form in which you have it in the integral case, where if you take a small piece in the differential form, you have d phi is equal to E dot ds. It's a dot product. So you know it, if you have any area, that area has a normal vector that's always perpendicular to that area, and you look at what the electric field is. Now generally the electric field might be at an angle to this area. Then you figure out what the angle is between the electric field vector and the normal vector to the plane. If this be theta, then you have E ds cos theta. Now ds is again a very small element. You find E dot ds over each piece, which if you want to find over the entire region what is the flux linked, you do the integration of that. You essentially add up all the fluxes through each of these small pieces of area. So this is the first method. Now for most cases that you will encounter, this electric field will not depend on which piece or which area you're dealing with. So quite often in your questions, this electric field part would become a constant, which means you would be more familiar with this formula of the electric flux, which is just E into A, which is just the electric field into the area. This happens when it's perpendicular. Firstly, the electric field is perpendicular to the surface, and also when the electric field is constant throughout the surface. So we have the first method. The next method is given to us by the Gauss Law, because the Gauss Law says that the electric flux linked with any closed area, a closed volume, is equal to 1 by epsilon naught times whatever is the charge enclosed in there. So it's the total enclosed charge, which means you have to add up all of the charges in there. Now I'll not go over this in detail. Obviously most of you know that if you have say plus 3q charge here, you have minus 2q and maybe another q here, then effectively you have plus 4q minus 2q. So your enclosed charge would just be 2q, the total sum of the charge enclosed. So that also gives you the flux, but mind you, this gives you the flux over the entire area. So if this is the enclosed, it's suppose a 3D structure and you have the entire part enclosed, so this flux is the flux over the entire area. Now how do you choose these Gaussian surfaces? What kind of Gaussian surfaces really help you with regards to finding the electric field? So the most ideal case would be if the Gaussian surface is symmetrical about the charge distribution. What do I mean by symmetrical? So suppose I have a positive charge here, right? My best Gaussian surface for a point charge is going to be a sphere around it. Why is that a good Gaussian surface? Because it's symmetrical. If you consider any point on that surface, that is always going to be equidistant with regards to that point. And what is the benefit of that? The benefit of that is that the electric field is going to stay constant all over this region. So when you eventually equate your E dot ds with your q by epsilon naught, you can effectively take this electric field as constant, get it out, do your integration easier. You'll get to this form in that case. Okay. And another case of symmetrical surfaces would be if you have a line charge, then you take the cylinder. You have done all of these, and the reason again, this very same thing, we want electric fields to be constant over that region. Now if it is asymmetrical, if you don't have a symmetrical option, if it is asymmetrical, then try to treat the given surface as a subpart of a bigger symmetrical surface. So we'll do a few examples of this, then you'll get an idea of it, that if it's asymmetrical, it's very difficult to calculate. So you have to consider that the piece that you want is part of a bigger symmetrical surface. So I'll show you an example of that. Let's move ahead to a few cases. Here it says that if a hemispherical body is placed in a uniform electric field, then the flux linked with the curved surface is. Now, at first glance, you would think that the curved surface has an area of 2 pi r square. The area of the curved surface is 2 pi r square. So, if you want the electric flux, then phi equal to E into this area, so E into 2 pi r square. But this is incorrect because that is not the flux linked with the curved surface. That is because over here the formula cannot be E into A. The reason being, at this point if you take, the electric field and the normal vector are in the same line. So you are good. But if you consider other points, then the angle between the electric field and the normal is effectively changing. So here you might have 0 degrees, so cos theta is 1. But for other points you have different values of cos theta. So this is the kind of case where you might have had to use that differential flux element and add them up. But there's a simpler way to do this. If you have constant electric fields, try to find what the area is with regards to that constant field, with perpendicular to the constant field. And the best way to do that is to actually look at the surface from the direction of the electric field. So I have this hemispherical bowl over here. Instead of looking at the electric field here, I take the hemispherical bowl. So the electric field was coming from that direction. So I look at it from the direction of the electric field. If I do that, what do I see? That is what I need to consider. If I look at that, what do I see? I see a circle. It will now become a 2D structure. It's now a circle. And what is going to be the area of the circle? The area of that circle is going to be pi r square. The area of that circle is pi r square. And the electric field is E. So the flux would be E into the area. In this case, you would say, why do I take the area here and not cos theta? Because mind you, if that is the area, electric field is in that direction, electric field is perpendicular to that area. So E into area would be E into pi r square. That would be the flux linked with this. So if it's constant, remember, only do it with constant electric fields that are in the same direction. Look at it from the direction of electric field. The area that you see, take that area and put it into E into A. That's all you need to do. Okay, but occasionally if the electric field is not constant, you need to go by the different method, by Gauss law. So here we have a similar example, but this time the electric field is radially outwards. So here I cannot use that method because the electric field is not constant and unidirectional. So the way to proceed with this is to go about with the Gauss law. We can assume that with regards to the Gauss law, if it were a complete sphere, then that sphere would have been symmetrical with respect to a charge over here. And that charge would have been able to create this electric field. So if I want to find what the flux is with regards to the complete sphere with a charge in the middle, charge Q in the middle, then that phi, let's call that phi complete, phi C, is going to be equal to E into your 4 pi r square, which would be the area of the complete sphere. Now over here, that is equal to Q by epsilon naught. If there were a charge, this is a hypothetical charge we are considering, so it would be Q by epsilon naught. Now over here, since we are dealing with half of that area, so now for this hemisphere, the flux is going to be half of the total surface. Because remember, this E into 4 pi r square, it can be thought of to be this plus the flux because of this. So the flux of this individual piece is half of this, which is E into 2 pi r square. So in this case, you have to treat it in that way. Think about what the flux is over the complete volume. Take that complete area and then take whatever fraction you want. This only works if you can visualize the electric field as being at a symmetrical point with respect to the complete circle. And this is what I meant when I said that if it's asymmetrical, see, if it's asymmetrical, the charge was here, it was asymmetrical. Consider that surface to be part of a symmetrical surface, then work with it. Okay, let's try one more here. It says charge is kept at the center of a cube. I want to find what the flux linked with any surfaces. Now again, if I treat of this surface, consider this surface, that's not going to be symmetrical because this point, the central point of the surface has a different distance, the edge of the surface has a different distance from the charge, so it's not symmetrical. But if I take this surface as part of another symmetrical as a larger symmetrical surface, which is the surface area of a cube, then I know over this entire cube, the flux linked for the entire cube would be given by Q by epsilon naught. Flux linked over the entire cube would be Q by epsilon naught. Now I can find this, because that is again a subpart of the bigger surface. Now bigger surface has to be symmetrical. So I've got the subpart. I know this flux has to be distributed evenly between all the 6 sides of the cube, because again it's symmetrical, so each side is technically the same distance away from all the other ones from the charge. So my flux here is 1/6 of the total one, because the flux because of each of the surfaces need to add up to this total flux. So this is again what I mean by if you have a asymmetrical surface, consider this as part of a bigger symmetrical surface. Another example is over here, where this time I have placed the charge at one edge. Now I want to find what the flux through the entire surface of the cube is. This time I can't use it as Q by epsilon naught, because again it's not symmetrical. Don't proceed by that. Construct another cube on the side over here, because as soon as you construct another cube on the side, now this charge is over here symmetrical. It's symmetrically in the middle of it, which means now I know that the total flux Q by epsilon naught is divided between this cube and this cube. So the flux through any one of the cube is going to be half of the total flux, so it will be Q by 2 epsilon naught. Alright. So here I have another question. Try to figure out whether you have to use the flux through Gauss Law method or you have to use the E into A method. So here it says a cone of base radius r and height h is located in a uniform electric field E parallel to its base. The electric field entering the cone is. So first up, right away I know I have to use the formula of E into A. How do I know that? Because it's in a uniform electric field. So now try to picture it. You have a cone. You have a cone over here and you have the electric field in this direction, because it says it's parallel to the base. Now again, since you want to find the electric field through this, best way to do is to visualize what the cone looks like if I look at it from the side of the electric field. Because if I look at it from the side of the electric field, then this cone is effectively going to look like a triangle. It's going to look like a triangle with a height given by the height of the cone, h, and if the radius of the cone is r, then the base of the cone is just 2r. Okay, it's given capital R, so let's keep it consistent. Capital R is given by 2r, which means now the area we can directly get, because it's the area of this triangle. Area is half into base, that is 2r, into height. Cancel out the 2 here, the area is r into h. And since we have used the method of looking at it head on from the direction of electric field, we can just get the flux as a product of the electric field and the area. So E into r into h. So the correct answer is E into r into h. This is the answer. So that is how you figure it out. You can use both methods depending on whether you've been given a uniform electric field or a non-uniform electric field. Use the method and get your flux through them. Thank you so much for watching this. I'll catch you all in the next session.